All right, everybody get their griddle cakes? Their galactic griddle cakes. Questions?
Morning.
Okay.
Yeah. Is this question for all you?
Sure.
Yeah. When you go ahead and use your for loop to traverse through the letters, and you find that no, why the letter when it's no, it's supposed to be updating that new node, right? Like so traverse that new node by making new node code that. Can you explain? Like I kind of understand it, but you explain why you do that?
Yeah. So let's start with kind of the worst case, which is where your root is just an empty node. Everything's pointing to null, and the string is a 0. And let's add the word hi. All right, so first thing you do, you go to the pointer corresponding to h, you look at it, you discover it's null, right? So you malloc a new node, initialize everything, set the end of string to 0, make all these pointers null, and then at this node that you were at before, you take that h, which is currently null, and you set it equal to the address of this new node. So you do something like temp equals malloc, and you do your initialize, and then root letters bracket, whatever index that was, just set that equal to temp. Okay, and then set root equal to that node, and you're done with the h. Go back to the top of your loop. So now you're going to check the I, and that's going to be null. So you're going to create a new node, properly initialized. You're going to call that temp. And you're going to take root that index, you're going to set it equal to temp, and then change your root to be there. And then you're done with the I, you go back and you check the next letter of your word, you're at the end of your word. So you come out of your for loop or your while loop, right? And your root is now pointing to this node after the last letter. This is where you want to set end of string to 1. So you can just do root EOS equals 1. That makes that a 1, and you're done. You've added your word. So follow these, and if they're not null, just move down to the next node and keep going. As soon as it's null, you can't move down to a new node, so make a new node, have it point to that, and then just do the same thing. Move down to that new node, keep going through your letters.
Yeah, I was not aware of like the whole new node.
Okay, yeah. Other questions? Yeah.
On the initializing of it,
Mm-hmm.
are you're running a loop in that? Is that everything to know, right?
Yeah, unless you like writing 26 assignment statements, which you can do.
Yeah.
But yeah, you want to set each of those letter elements to be null.
So that would just be, we just put 26 in it, right?
Yeah, like for I equals 0, I less than 26, I plus plus. And then set arrow EOS equal to 0. In reality, those will be initialized to 0 already, but always get in the habit of setting them up explicitly. Yeah?
Why is that no?
Because when you create a node, you want all of these things to initially point to null. Because if you don't initialize it, and this happens to have a value of, 17 here at the letter G, if you happen to search for the word HIG, you're going to say there's an H, there's an I, G points to location 17. Let's check location 17, you're going to segfault. Right, so if you don't have something stored, you want to make sure that each of these pointers is initialized to null. Because that's how you're telling that there's not a word stored. Right, same way you want to set the EOS to equal to 0, because that's how you're telling that there's not a word that ends there.
So yesterday when I was doing ODP, instead of setting the EOS on the next node, I set it on the last letter, and it worked. It gave me 10 out of 10.
Yeah, I tried to make test cases where that wouldn't happen, but I might not have succeeded.
In general, it'll always be the node.
But the problem is if you add the word high and you set a 1 right there, then if I search for an H, it's going to tell me that H belongs to your structure. And I thought I had checked that, but I probably didn't. So yeah, set it on the node after the last letter. Because if you do this, if you do an HI and you store it there, and then you want to store the word HK, right? What can I do to tell me that I've got an HK as opposed to an HI? Right, so that's why we have this point somewhere else. Set that to a 1. Other questions? How's PA4? We got lots of people doing deletion right now, which is cool. Words can't explain your feelings about PA4.
Start Thursday night.
Yeah, good. Or Friday morning. You get up at 5 and you got 3 hours. All right, let's talk about heaps. I love heaps. Heaps are binary trees, but they're not binary search trees. They're kind of like a lazy binary search tree. But they're going to do some wonderful things for us. And there's 2 types of heaps. There's what's called a max heap and there's a min heap. And they're symmetric to each other. I'm going to talk about max heaps for now. But if you want to do min heaps, nothing really changes except the order in which we do things. So largest and smallest gets swapped and so on and so forth. So we're going to mainly talk about max heaps. But once you know these, you know min heaps too. So a max heap has 2 properties. It's a binary tree. It has 2 properties. So property 1, each node is larger than its children. And there's no left-right distinction made here. It's just got to be larger than both of its children. Property 2, the tree is completely filled at all levels except possibly the lowest. Which is filled from left to right. And that's really all we need for a tree. So let's just look at property 2. What do I mean by this tree being completely filled at all levels? So that's completely filled, right? Each level has the most nodes possible. This is also completely filled. This is not completely filled, right? Because I could have some nodes here and here, right? And this lowest level is allowed to be not completely filled because you may not have enough data to fill it, right? A tree always holds 2 to the n minus 1 things when it's completely full. You might not have 2 to the n minus 1 things, but the only place you can have space is in this lowest row. And this lowest row itself has to be filled in from left to right. So this is considered completely filled, right, in a heap-like way. This is also valid in a heap-like way, but this is not. right? Because every level is filled except for the last one. That last level has to be filled in from left to right. So I should have something right here before I have something over here. So if you were to scan this thing from left to right, moving down from top to bottom, once you run out of nodes, you should be done, right? You should have hit every node before you get to an empty spot. And property 1 is sort of self-explanatory. Every node's bigger than the value of its children. So what do max heaps and min heaps? This just changes. Every node is smaller than its children. Property 2 is the same. So what's a potential max heap? 40, 30, 25, 15, 28, 2, 1. Bless you. All right, so that's a valid max heap. And it's kind of weird looking, right? So here we've got something larger on the left. Here we've got something smaller on the left. So no requirements about left-right values relative to each other. We've got a 28 here. We've got a smaller 25 up here. That's perfectly fine. We've got a tiny little 1 down here. We got a big old 26 at a deeper level. That's fine. The only requirement is each node has to be bigger than both of its children. 25 is bigger than its children, 30 is bigger than its children, and so on. But we get some nice properties from this. For example, since we know that 40 is bigger than both of its children, 30 and 25, and we know 30 is bigger than its children, and those children are bigger than their children, and 25 is bigger than its children, we know 40 is bigger than anything in the whole tree. Right? We could prove that pretty easily with mathematical induction. So in a max heap, the largest number in the tree is always at the root. And that's a nice feature, because if you want to find the largest element in the collection of things that are stored as a heap, it's just the root. So we do different things with heaps. Sometimes we use them to organize information where we want to grab the largest thing one after another. This is what we do with like a priority queue. We might take the priorities of all the jobs and put them in a heap, and then if we want the next job with highest priority, we can just grab it from the root of the heap. But they're also a really efficient way to sort data. All right, so this is an example of a heap, and we'll work with this one because I like this heap. I feel good about it. So let's remove the largest element. So how do we remove the largest element from the heap? Well, we know the largest element is at the root, right? So the root is the largest. So we can find the largest easily. But if we're going to remove 40 from the tree, we don't really have a tree anymore because we just deleted its root, right? So we got to put something else in its place. And if we try to do something like go down here and find the largest thing in the left subtree or something like that, right? Anything that we decide to move into the root is going to leave an opening somewhere in the tree. If we just pick up this number 2 and we move it up to the root, right? This is no longer a heap because we just created a hole in this level up here. So we can't remove anything from any of these upper levels. We can only remove something from the lowest level. And if we remove any of these things except the last thing, it's not going to be a heap because that lowest level won't be filled in from left to right. So we're going to remove the root and replace it with the last element, by which I mean this 26. So we're going to come up with a new structure where the root is now 26, 25, 2, 1, 30, 15, 28, 10, and 12. Now it still has the right shape for a heap. Completely filled in except the bottom row, which is filled in from left to right. But it potentially violates the heap property. In fact, right at the root, 26 is not bigger than both children. Okay, so now we're going to do one more step, which is called down heaping. So how do we down heap? Start at root. Swap with the largest child. And repeat. Okay, so we start at the root. 26 is not smaller than both children. So we have to swap it with the largest child. Sorry, not bigger than both children. Swap it with the largest child, which is 30. So this becomes a 30. This becomes a 26. Repeat the process. Compare 26 to its children. Swap with the largest child. 28 is the largest, so this becomes 28. And this becomes 26. And 26 has no children. We're done. Bless you. And we've got a heap. Right? Every node is bigger than its children, and it's got the proper heap shape. And guess what's at the root? The largest thing in the remaining values on the tree. So let me copy this. Alright, so if we want to remove the next largest value, we're going to take off the 30. We're going to take the last element and put that up at the root. And then we're going to swap that with the largest of its children. So that would be a 28, so put 28 there. Put a 12 here. Swap that with the largest of its children, which is 26. And here it does not violate the heap property because it does not have a child that's larger than itself, so we're done. So now our heap looks like this. Alright, let's do one more. Let's remove the 28. So that goes away. We put the last element on the last row, which is a 10 up here, and then we down heap. So if this already is the biggest, if it's already bigger than both children, we're done. Okay, but we check and it violates the heap property, so swap with the largest child. So there's 26 and 10. That violates the heap property, so swap with the largest child. And we got another heap. And we just keep doing this all day. So what's the order of complexity of this removal operation? If we want to remove the largest element from the heap, how many steps does it take roughly, depending on the number of elements n? Yeah, it's the height, because grabbing the last element, putting up here, that's just one operation. And then potentially we have to make an adjustment all the way down till we get to a leaf. And the longest that might be is the height of the tree. So height of a tree, if the tree is nicely filled in like a heap has to be, it's log n. So 1,000,000 pieces of data stored in a heap and you want to find the largest element, it's 20 operations. Well, finding the element takes one operation, it's at the root, but then doing what you have to do to prepare for the next one, 20 operations. So very efficient. And if you have your data stored in a heap and you want to print it out from largest to smallest, it's log n to find each of your n numbers in the right order, and you have n numbers, so that's n log n to completely remove everything from a heap in order. Alright, so that's deletion. Let me show you insertion, then I'm going to have you do this yourselves. in some examples. So let's just continue with our current heap, which is 26, 15, 25, 2, 1, 10, 12. And let's do an insert. So add number after the last position, and then upheap. Okay, so add number after the last position. If there was no 2 or 1 here and we wanted to insert, we would put the number right here. If there was a number there but nothing right here, we would put the number right here. If we're adding a number and this bottom row is completely filled up, we start a new row and we put it in the leftmost position. So what should we insert? Let's insert a 30. So we're going to add it down here in the leftmost position of the bottom row. And then we're going to upheap. Upheap is kind of the dual of downheaping. So how do we upheap? See if the parent violates the heap property. If so, swap with largest child and repeat. All right, so we just inserted a 30. Its parent is 10. Does 10 violate the heap property? Yes, 10 is not bigger than all of its children, so swap. This becomes a 30, this becomes a 10. Check 30's parent, 15. Does 15 violate the heap property? Yep, so swap with the largest child, which is again 30. Go to that parent, 26. It violates the heap property, swap with the largest child. And you got a heap. Let's see. Let's just insert a 20. So we put a 20 down here, check its parent. Parent is not bigger than both children, so swap with the largest. Check its parent, 20, 26 is bigger than both of its children. Heap property is satisfied, we can stop. And this is also order log n. Putting a number down here is a single operation, and then potentially you have to upheap all the way to the root, which is log n steps. And there's no issue of balance here because the tree is always as full as possible, right? That's the second heap property. So we don't need to worry about, there's too much stuff on one side or the other, or this is really long and skinny and so on. It's always going to be log n. All right, you ready to try this? All right, find a friend, find a board, and let's build some heaps. For try? No, try we just follow a pointer based on each letter. Yeah. No. All right, so start with an empty heap and go ahead and add a 20.
so we don't run out of space.
All right. So looks like everybody's got a heap with a 20 in it. Good. All right. So let's add 10. And this is a max heap.
Oh, no. I don't want to do
All right. So everybody's got a 20 and a 10. Let's add 15. All right, good to go. All right, so let's go ahead and add 40.
This is 40, and this is 20.
Good. You're up heaping. Good. 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 Good.
Why are you the diet? Just diet like you.
All right, cool. So looks like everybody got this. All right, let's go ahead and insert 25.
You want me to write? 5. That's good.
Right.
Okay. 40.
Board wars.
Board wars. Good. 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 Good.
Big small spot is blood.
Yeah, don't change the order unless you have to.
Yeah. This one's a lot easier compared to what we're
The thing with yesterday, we were doing it. I was with the second one, and it was just one line missing. He didn't do it. That's why it didn't work. He had it today. He told me what he did. Tried it.
All right, so go ahead and add 3 more numbers of your own choosing one at a time.
Okay.
So before we make some room.
It's really hard.
So we have to add 3 numbers, right?
No, you just say choose it. Okay, let's begin with one. No, one. We begin each one by itself. You don't have to write.
Oh, that's right. You have to do everything step by step. So
Step by step.
Yeah.
Just one.
So now you have to figure out how to. Oh, you know.
No.
It stays the same because
Still
one
here.
is less than 15.
Yeah.
Oh. didn't know what I wanted to do. Okay, that changed even now. 100.
Yeah.
You want to change it to 100? Now it goes to 15. Yeah.
15 and 100 to 40. What?
No.
What are you doing?
If this 100 is bigger than this 40, so you have to put it.
You almost forgot.
Yeah, you need to have 100, 40, 40.
Another 40?
Because
No,
this is your read.
Oh, I thought you needed that.
No, not yet. 40.
40, no, 40. Because 40 was originally your root, so you put the what's
And this 50.
Yep.
That's it.
I thought you were talking about this one. And you know,
Now let me do mine. Okay, 50. Okay, let me write it down.
That's different.
50, which is bigger than this. And we move.
So did you add in 3 more numbers?
Yeah.
Okay, so then go ahead and start the lever whenever
100.
Yep. Down and make sure that you're pulling off.
50.
So now it's my turn to add a 43. And this one, this one becomes a 43. One side.
What do we do next? We have to
Swap it with the bigger one.
Yeah.
Oh, right.
Why you make it up?
25.
yeah, air.
You can't even tell them.
That's me.
I wrote my numbers 90, sorry.
Okay. 1 to. But we should cut it just to show it. Just like the race stuff. He's always like that. I remember last time I remember when we were doing a project for physics. He was doing solution and he did something good, right? After that he just like, oh no, we need it. And after that, he got what we did.
Reading is give the good opportunity to do it.
To suffer more, yeah. Exactly. That's what the point is. No, because because they left everything. Us we didn't.
See how detailed it is.
Oh, right. So you only delete the root.
Okay, let's do more numbers.
So we delete 200. The only thing you delete from the start.
Just right here, swap.
From here, 200.
Oh,
Another.
yeah.
Here, 200.
And now we
This
start
is
flipping.
small.
Swap.
Slab here. And here will be 200. And slab this.
I picked up a copy of the red team and the blue team.
200.
Swap.
They got printing on the blue team one.
Wait, don't wait. Do it fast. Do it fast.
You guys gotta do it one step at a time. It's simple
I
stuff.
won't fix everything at once.
So you.
So don't forget to change this to
I mean, let's keep it.
And now you download the 6. Swap with the bar.
Okay, 200.
Take the last thing on the last one.
Yep.
That's how we do it.
The color even look different.
No, this way. When you start,
You can't erase your step because one can be crossed.
He thought our first number is 0, 0.
Because-
Second number.
okay, you understand. He want you want to see what you.
Well, I'm trying to make sure he doesn't understand. Confuse him.
What?
Confuse him.
No.
All right. That's the text message you're using here, right?
One.
Oh, okay. Okay.
You want to do more numbers so you can?
Negative, two negative.
Oh, how about negatives?
Well, if we
We
put
should ask for
negative,
it.
Do the multiply on
it just stays in that spot.
That's a slow.
the very last
It's like, get right straight.
So you would delete this one first.
Correct.
I mean, if it says that.
Peter
And yesterday I was talking about like the concept for the short answer question. So I mean the long answer question would be if
This is not no.
I got lost. I got lost. I said, what the hell is he talking about?
Like short answer.
Right, but before.
Usually like two, and he do
Our base
long
case is
answers, two,
if
and
left
he
is
do
zero, or if
multiple.
right is not no.
Even then, it's still
He
difficult.
want you to understand the
So
concept.
if you're
Deleting.
so question. So for the last one.
Actually, I should
not
cook it
a binary
with.
tree, but something like this.
I am having favorites.
So you can do
I heard so
as long
much.
so
You know,
as long as the right
60
something is
receive 60%.
No, it's there's no special case there, so you're trying to delete the
Until now, I'm a little bit below 60.
So delete the 7, replace it with the last thing.
After the exam next week, I
You
mean
always
this
go out
week,
of the last
Wednesday, I
row
think
and you
maybe.
move over to the
The grade will know.
How many midterms does he have?
3. Same. But last time I was asking him, he said
this
4.
one.
So you only delete the
Because we do
7.
the exam together. I went to the first test, I said,
Right.
no way.
Yeah. Because you always want to have this shape where it's filled in except for the bottom. The bottom. Okay. You deleting stuff okay?
We haven't started deleting stuff.
Okay, so you added stuff.
Yeah.
Okay, so you got 200 up there, 150, and that looks like a beautiful heap. Alright, so delete the 200, turn it back into a heap, then delete the root again, and keep doing that, and you should end up getting your things in decreasing order.
Okay.
So basically, we delete the root and then we switch it with the last one, the last of the elements.
Alright. Yeah.
Which is
Alright, so keep going
20.
to 40 and keep deleting, you should end up getting all of them.
So this one becomes 100 on this side, yeah.
Ours are not changed.
Yep.
And now you have to order.
Yeah, we don't have to order.
No, wait. How we order it back? Wait.
Let's keep it. Let's talk about the whole thing.
No, we have to understand. Okay, and after doing this, where we go? We go here again, the bottom, or what?
Oh, we go from top to bottom. We start at the root, and then we just go from top to bottom.
And now we organize it.
So let's see, we already switched these to 25, 100, and then we look at
143.
25 and 43, and these flex, this becomes 25 and 43. This stays the same, we don't do anything with this, and the 10 is smaller than
And then this is, yeah, wait. That's 25 made an accident.
We're good.
Anyway, and after that, what? We deleting more?
Yeah, let's delete everything.
But
That is left to right, yeah.
Wait, hold on.
Hopefully overnight.
relax, delete 100. Then we go.
Then you try to have fun.
Here we have
The
10 gone.
no,
10
100.
over here.
Yeah.
Okay. Now we switch.
This is 50.
Okay.
Or is it?
Thanks to my
That's the message. We switch it with what?
Okay, so now we look at the 10 and the 43 and the 50.
Oh, it's really beautiful.
Well, I don't know which one to do first. This one first?
Thanks, Rob, with 42.
And then we'll go the left branch and then the right branch later.
Okay.
Got it. Let's see.
And if we switch with this,
Test over 3 Bibles.
wait a second. Step by step.
Everything one step.
No, I don't like it. Anyway, 25, right?
Yes.
Three, no. 43. 25. I have to look now. I have to switch. Now here
Okay, so we wanted to ask you if we went through the correct process.
For deletion?
Yes, deletion.
Okay.
So we decided to remove the 100.
Okay.
And so we took the last element and got out of the root.
Okay.
And so then we decided to only just like look at the left branch for now and switch the 10 with the 8. And then we kept going down and then we look at the right
No, you want to do it at the same time.
at the same time.
Yeah. So you want to compare this to both children, and if it's not bigger than both, swap it with the largest child.
Oh, so let's go back and read it.
Okay.
Great stuff.
see the 10 will be here.
Yeah.
And it's gone.
Yeah, so now I have to look at simultaneous.
Okay, then here.
Then the 50
Switch
will
here.
look with the, yeah. With the
Last year.
Here. Okay, this one.
that becomes the 40. So now we look at this.
Nope, you're done.
Oh.
No, because this is smaller than this.
You start at the root, right, and you swap with the largest child, and you keep moving down until the heap property is not violated.
Okay.
You got down to a 10, that's not smaller than its children, so you're finished.
And if you look at it differently, so this is bigger.
Yeah. So that'll automatically satisfy as long as you swap with the largest.
That
That tree
goes
will
by
be
my
like
graph.
40.
There you go. Perfect. All right, so I think everybody's got up heap, down heap, and removal and insertion, which are the basic heap operations we perform. So there's two other things we want to talk about with heaps, and we'll get into this tomorrow mostly. One is, how do we create a heap? Because if we want to use a heap to sort information, first we need to take a bunch of numbers and turn it into a heap, and then we can do this removing the root successively. And we know that removing the root, it takes log n for each number, and so it's roughly n log n once you have a heap. But how do you build a heap? And one way to build a heap is to just take your numbers and insert them into an empty heap one at a time, like you did in the beginning of this exercise. and then go ahead and delete. But it turns out we can do something far more efficient. We can build a heap in, I think it's log n operations, average. So we'll go through that algorithm. The other thing we want to talk about is how do we actually implement these? And certainly we can implement this with a struct node, which has a left and a right and a data value. And we can just treat this like a binary tree. But it turns out there's a much easier way to do this. And remember, we need to do things like find the last element on the bottom row. And that's kind of tricky to do in a tree, because you start off, you don't even know from the root whether you should go to the left or the right. If my heap looks like this, my last element's going to be in the left subtree of the root. But if my heap looked like this, my last element would be in the right subtree of the root. And that's going to change as we add or remove things to this heap. So as a regular binary tree with a left and right child, it's not totally clear how to find that last element without doing a bunch of searching, and that can potentially ruin your performance. So we're actually going to go back to implementing these things with arrays. And it's going to come out really beautiful. So suppose we have a heap like this. And suppose I store these in an array. And I'm never going to use element 0 in my array, but I'm going to store these things in breadth first order. As so. And I'm going to have some sort of variable that tells me how many things I have stored in my heap. And anytime I want to get to the last element, it's just index last. So if I add something, I'll increment this. If I subtract something, I'll decrement this. So it's really easy to find the last element in the heap. The other thing we want to do is we either want to find our parent or we want to find our two children. And with a struct node pointer, right, that's easy because we have pointers to the left and right children. We could add a back pointer for the parent. But it turns out if we store our nodes like this, finding parents and children is really, really easy. So I'll leave it at that and look at the cliffhanger ending, and we'll talk about how to do that tomorrow. But if you play around with this, you'll probably discover the magic for finding parents and children when you store your heap like this. All right, so I'll see you tomorrow.